Chapter 2, Section 2. In this section, we look at how we can graphically represent a derivative and how that relates to the mathematics behind it. The derivative of a function is the slope of the tangent line to that point. So by looking at the graph, we can draw in tangent lines and estimate their slopes to get a good estimate of the derivative at a point. Let's look at the figure below to get a good idea of how we draw in tangent lines. We're going to look at the tangent lines at the points x equals -2, x equals 1, x equals 0, and x equals +2. So you would go to the point x equals -2, go up to the graph, draw on a dot. Then you want to draw on the line that touches at just that one spot. That's called the tangent line. So the slope of that line is the derivative at that point. So we've gone ahead and drawn in the tangent lines to each of these points. Now let's see what we can do to find the derivative. We want to look at each of these points and estimate the slope of each of these lines. So let's look at the first one. The slope of the tangent line at x equals -2. If you look at it and try to estimate the rise over the run, so how much it goes up over how much it goes over, we can say it's approximately 1. For every 1 unit it goes up, it goes to the right 1. So we would write this as f prime of -2 is approximately 1. That means that the derivative at -2 is approximately 1 because that is the slope of the tangent line. Similarly, we can look at other points on here. So when we go to x equals -1 and we estimate the slope of that tangent line, I found it to be approximately 0.3. So that means f prime at -1 is approximately 0.3. When I went to the point x equals 0, I went up, drew my tangent line, and now you can see that it's negatively sloped, so I estimated that slope to be approximately -0.5. So I can write that as f prime of 0 is approximately -0.5. And then lastly, when x equals 2, I drew in the tangent line, and I approximated that slope to be approximately -1, so f prime of 2 is -1. Remember, the slope of the tangent line is the derivative at that point. Something very important that you want to notice here that we're going to use quite a bit is that whenever the tangent line has a positive slope, the function is increasing, and whenever the tangent line has a negative slope, the function is decreasing. This works in both directions. So if you have an original function and it's increasing, which means it's going up as you go from left to right, the tangent line slope should always be positive. And if you're decreasing on the original function, the tangent line slope will be negative. So we're going to call these the three basic rules. If f is increasing on an interval, the derivative will be positive on that interval. If f is decreasing on an interval, the derivative will be negative on that interval. And if f is constant on an interval, the derivative will be 0 on that interval. So let's look at these two graphs and see how these basic rules translate into these graphs. The graph on the left is the original graph of f of x. So here, we want to see where this is increasing and decreasing so we can apply our rules. If you look between approximately x equals -3 and x equals -1, you will see that it's decreasing. It's going down. So we expect that our derivative should be negative on that interval. Well, if you go over to the derivative graph on the right, you will see that between -3 and -1 it is indeed negative because the line is below the x-axis. Then, if you go back to the original, between approximately x equals -1 and x equals +1, you can see that it's increasing because it's going up. And we know that wherever it's increasing, the derivative will be positive. So if we look on the derivative graph between -1 and 1, you'll see that it is indeed positive because it is above the x-axis. And then lastly, between x equals, I would say approximately 1 and 3, you can see that it's decreasing. So on our graph of the derivative between 1 and 3, we should be negative, which we are because we're below the x-axis. So these rules are certainly worth keeping in mind and writing down because they do come up in a lot of ways. And these are the basic rules that we'll be using for the rest of the semester to translate back and forth between graphs. Now, there's one special case. Although most of our graphs will be of this form where they're curvy, we do have the case where the graph is a line. So let's look at that simple case and see how we apply it there. If your graph is a straight line, the rules still apply. So we're looking at increasing and decreasing first, and then if it's constant or not. So here, and we look at our graph on the left, you can see that it's decreasing because it's going down. So we expect that our derivative should be negative, which just means it's below the x-axis, which if you look at your derivative graph on the right, you'll see that it is. However, if you want to draw a tangent line onto a straight line, it will be right on top of the line because it'll touch right at that one point, but also all the points on the line, which means that every single tangent line you draw on a line will have the same slope as that line. So here, if our slope was approximately -3, when it translates into the derivative graph, it'll just be the graph y equals -3. So you need to remember in this special case that the tangent line of a straight line will lie on the line. So that means, again, it will be a constant and have the slope of the original graph. Now would be a good time to go ahead and try some of the homework from Chapter 2, Section 2.